Hi everyone, welcome to tutorial 8, buckling of columns theory. So just now there is a FBI warning. In this tutorial we will put our stress on differential equations as well as proving the column related equations by using differential equations. So if you want to get some more practice problems for the column deflection, then you can go to tutorial 9. So for this tutorial, I will not really talk any single details to you or everything. I will show you some of the techniques of solving differential equations, as well as show you how to solve the buckling equations in the Euler continuous model by using differential equations. Okay, so there are 4 models in total, but 4 models representing 4 support conditions, but I will only describe you 1 or 2 which are particularly difficult. Okay, so we will also leave you an exercise which is about columns with eccentric axial loads. So you can try to use differential equations to solve for the deflection curve, the critical load, etc. for the columns with eccentric axial loads. Okay, so there is no problems in this tutorial, so if you are really interested to problems related to column, you can go to tutorial 9. But still, I wish you to watch a couple of slides on how or what is column, or how could we compute the critical stress of column. So you can stay here and have a look. Okay. So first is about differential equation fundamentals. So if you would like to learn more about differential equations, I would recommend you to find some information from Professor Chesnoff. He is a very good professor in math department of HKUST, so following is his link. Okay, so if you want to learn more about ODE, the ordinary differential equations, you can find the information below. Okay, so here in this tutorial we are going to prove the column related equations by using the knowledge of second-order linear homogeneous or inhomogeneous ordinary differential equations ODE with constant coefficients. Well, I'm not showing off, but well, the name is long, but you are not supposed to memorize the name, but you are going to memorize some fundamentals of second-order constant coefficient homogeneous ODE. Okay, so to solve this differential equation, which is given by a x double prime t plus b times x prime t plus cx t equals to 0. So let's first have a look on how could we classify this ODE. So it is an ODE because there is only one variable t. Okay. And also it is of second order because the differentiating order of the term with the largest differentiating order is of the second order, x double prime. X is differentiated twice. Okay, and it is constant coefficient a, b, and c. And this ODE is homogeneous because on the right hand side of it, it is 0. So in case on the right hand side it is some number, say 3 or t squared or 2t e to the power t, something like this. If there is anything, non-zero things on the right hand side, then it will become inhomogeneous ODE. Okay. So let's first talk about the homogeneous ODE case, because the inhomogeneous ODE case is rather similar to the homogeneous case, but anyway, solving a homogeneous one is the fundamental. So to solve these differential equations, we will have an educated ansatz, which is an educated guess that the solution x equals to exponential of RT, where R is a constant. We are going to solve what is the constant. Okay, so substitute x equals to exponential of RT into the ODE, then this ODE will become something like this. Okay, so the x double prime is r squared e to the RT, and x prime equals to re to the power RT, and xt is just ERT. And you put it inside, you can find that all those three terms will now have something like ERT, which is convenient for us to cancel it out. Okay, so once we cancel everything about ERT, the thing left, which is AR squared plus BR plus C equals to 0, is a characteristic equation. Okay, so it is a quadratic equation of R, and we call it characteristic equation, and by using our knowledge in quadratic equations, we can quickly solve for R. Okay, but the thing you are going to bear in mind is that although we have R over there, but the value of R in differential equations course could be real, the two distinct real roots, or complex conjugate roots, or both of the roots are repeated real roots. Okay, in those differential equations related to column, the symbol of determinant will often be negative, which means you will have complex conjugate roots. Okay, but anyway, when we are solving some differential equations, the symbol of the determinant here is actually a very important factor, and it will lead very different solutions of second order constant coefficient homogeneous ODE. Okay, so after solving the characteristic equation, you will be able to get two roots R1 and R2. The roots R1 and R2 could be as what we just mentioned, could be two distinct real roots, or repeated real roots, or complex conjugate roots. So after we get R1 and R2, you will get two results, which is x1 and x2. x1 equals to exponential of R1t, and the exponential of R2t is x2. But it is not the final solution. By using the principle of superposition, we can have xt equals to something like this. That is, any linear combination of x1 and x2 can be the solution of the differential equation. So what we need to do is to solve for C1 and C2 in order to get the exact solution for this differential equation. The solution of second order constant coefficient homogeneous ordinary differential equation, as what I mentioned in the previous slides, is highly depending on the symbol of the determinant. For example, if the determinant is greater than 0, that means for the characteristic equation, there are two roots which are real and distinct. Then we can get the solution directly by using the superposition, which is xt equals to c1 exp r1t plus c2 exp r2t. Another case is that when the delta equals to 0, the determinant equals to 0, that means the characteristic equation only gives you one solution. So since in the second order C.C.H.O.D.E, we need two solutions so that we can have a linear combination of two things. So we have to make up another solution, but by our educated guess, and which is verified by mathematicians, the second solution is simply t times exponential RT. Okay, so the solution when delta equals to 0 equals to C1 e to the power RT plus C2 t times e to the power RT. Well, although those two cases very often occur in other contexts, but for our course, the most frequently observed
is case 3, where delta is less than 0.
In this case, we have to deal with a little bit about the complex numbers. So for the complex conjugate roots of characteristic equation, we will use the following imaginary and the trigonometric relationship to convert our exponential terms with imaginary power to cosine and sine things. Okay, so in case delta is less than 0, we have to use the relationship that e to the power I theta equals to cosine theta plus I sine theta. Okay, so for this equation, you may want to check Chresnov's textbook. Okay, so basically from this equation we can write cosine theta equal to something like this, and sine theta equals to something like this. But by superposition, all those things can be written as exponential of the real part times C1 of cosine t times the imaginary part plus C2 sine of t to the imaginary root, imaginary part. Okay, so among those three cases, case 3 is most important in our column problems. But well, if we only say the solution is this, then you will not know how are we going to solve some differential equations. So the following follows an example of a second order constant coefficient ordinary differential equations, which is homogeneous. Okay, so for this differential equation, there are two initial conditions, which are given here. So to solve this differential equation, what we do is that we set x equals to e to the power RT. Then the whole equation will now become something like this. Then we cancel out all e to the power RT to get something like this. R squared plus 4r plus 5 equals to 0. Well, to solve this quadratic equation, we have r equals to 2 minus b plus minus 16 minus 20, which is minus 2 plus minus I. Okay, so we have two roots, R1 and R2, which are complex conjugate roots. So once you get R equals to minus 2 plus minus I, then some of you might think of, okay, you could have a solution that xt equals to C1 e to the power RT, so t times minus 2 plus I plus C2 e to the power t times minus 2 minus I. Some of you might say, okay, this is also a solution by using the principle of superposition. Well, it is correct, you are correct, but as an engineer, this term does not make any sense to me when I am doing any engineering problems. So what we do is that we try to make the solution to be something like this. Okay, so this time, instead of using the equation, which is here, which is here in our previous slide, what we want to do is that I will show you how could we obtain a solution. So to obtain a solution, first we take out the real part of this power. Okay, so for both of e to the power t something, you have minus 2t that can be taken out. So I write here, at equals to e to the power minus 2t, bracket c1 e to the power it plus c2 e to the power minus it. Well, so far you could have no idea about why there is something like this. Why do we want to write the things in this way? Well, the reason is that we want to apply those two equalities, cosine theta here and sine theta here. Okay, so as you can see here, it is just some process of superposition. Cosine theta equals to something one half of exponential of I theta and 1/2 of exponential minus I theta and so on, right? And the same for sine, it is just some superposition. It is equal to 1 divided by 2i exponential of I theta minus exponential of I theta divided by 2i. So here it is, we are just doing another time of superposition and rewrite our solution to be beautiful. So here we have EIT and e to the power minus IT. So what we can do is to rewrite it as e to the power minus 2t c1 cosine t plus c2 sine t. So still, as we mentioned, c1, c2 are just arbitrary constants, right? So we can totally, by using the principle of superposition, to rewrite the solution in this way. So this is what we want, and what's next is to solve for c1 and c2. To determine c1 and c2, we will use the boundary conditions, which is located here. So let me use a different color. So now you are going to use the boundary condition, which is located here. So substitute into xt, and probably you need to differentiate xt once again to get something else. Now you differentiate xt and you got x prime t, okay, because once you differentiate it, you can use the boundary, you can use the initial condition, which is x prime 0 equals to 1, and you substitute it into it, and you get something like c2 equals to 3, and you substitute this one, and you substitute this one into our equation, then you will get c1 equals to 1. So after you're solving for c1 and c2, now you can get the exact solution of the second order constant coefficient homogeneous ordinary differential equation, which is exponential of minus 2t, and inside the bracket it will become cosine t plus 3 sine t, so it will be the solution of this problem. Okay, superposition will always occur in our later derivation of the Coulomb equations. So here it is just some warm-up and provide you some basic ideas on what differential equations is and how could we solve differential equations. So now let's go to our core of this chapter, which is columns. So columns are widely used in buildings and structures. For example, in the background, you can see here is some columns. Okay, so there are a lot of columns here. They are all supporting the ceiling of a building. So you can imagine this is the ceiling. It could be very, very heavy, and below it there are so many columns that are supporting its weight. Okay, a lot of them. So now we are going to study the mechanics of those columns in between. the failure of columns is very hard to be detected because the column deflection problem or the column buckling problem is actually not a kind of deflection problem or the extent of deflection or the stressing side. It is about the stability problem. If the load inside the column is too large, that is larger than its critical load, then the column will suddenly or very rapidly be destroyed, and it can be very hard to detect. Also, the high temperature will further reduce the strength of the column, okay, and it will, so particularly when a building is on fire, so there is a fire alarm in the building, and the material of the column is heated by the fire, then the column will become even brittle, or later on it will be even easier to be broken. Well, here is something from my past lab report. So it is an experiment talking about when there is a column which is simply supported, a beam like this which is simply supported, and we add load P onto this column, and we are measuring the deflection in the middle, in the midsection of this beam. So the horizontal axis is talking about the deflection, and the vertical axis is talking about the applied load. Okay, so as you can see, the deflection of a column in the midsection increases rapidly as applied load reaches some certain point. For example, from this point, this is about 700 something, around 750 Newton, right? And once we apply a little bit more load, say 750 to 850, then the deflection could increase very rapidly. As you can see, from here to here, the deflection suddenly increased by 2.25 millimeters. And by this trend, you can observe that once the applied load onto a column reaches some extent, then the deflection could increase in a very terrible trend, that once a load is too large, that is larger than some critical load, the deflection of the column could increase very rapidly, that bring you very large danger. So as you can see from this plot, the deflection is actually a kind of stability problem. That is, once your applied load is less than some critical value, then your column can withstand normally. But if your applied load, say for example for this specimen, if you apply a super large load, then I believe this column will suddenly be destroyed. Okay, so here you can also see, so it is a plot still from my past lab report. So once the load becomes so large, it will make the deflection increase significantly, and as you can see, it is of 5/6 of the critical load, which is about here. Okay, and even the applied load is arriving 5/6 of the critical load, the deflection was still very small. But once you apply a little bit more load, then then the deflection will increase very rapidly. Okay, so the same for this one. It is about 5/8, I guess, and 2/3. Okay, around that level. Then still, to some extent of critical load, the deflection was still very small. But if we approach and make the column exert a load which is near its critical load, then the deflection will increase significantly. Okay, so the column deflection could be a very dangerous thing, because once a column is going to buckle, you have no idea about when will it buckle, because you don't know for the time being what is the load applied on the column. Once it becomes a buckled column, then the whole things will be different. Okay. So next, let's discuss about some models of column mechanics. So there are a lot of different models we would adopt to study the filling mechanism and the performance of columns. So in this course, we cover three models, three big categories. Okay, one is the simple model, one is the Euler continuous model, as well as the column with eccentric axial loads. So basically, those two categories are similar. So they are all about continuous model, but one thing is that for the third case, there is some eccentric axial loads. So for this axial load, I will not prove for you. It is left to you as an exercise. As long as you are solving the differential equations correctly, I believe you can get the results correctly. Okay. So basically, we have a simple model, which is a column is approximated by two sections of rigid bars that are held vertically by a rotational spring. Also, there is Euler continuous model, which is each column is treated as smooth continuous curve, and columns within four distinct boundary conditions will be studied. The name Euler is due to the need of solving Cauchy-Euler differential equations. So just now we have solved some differential equations, ODEs, right? So this kind of ODE is called Euler differential equation due to the need of set x equals to ERT. Okay, so certainly there are some other differential equations that enable us to solve, but anyway, for this tutorial, we will concentrate on the differential equations related to columns. Okay. So the first thing is the simple model of buckling. So still, it is like two rigid bars over here, okay, and they are supported by a rotational spring of constant beta r, okay. So once the column is being bent, the angle of rotation in the middle is 2 theta. So as you can see, even though here we measure 1 theta, okay, but by alternating angle of those two parallel lines, we can see here is in theta, here is a theta, and the total deflection of the spring is given by 2 theta. So eventually the spring moment is given by 2 theta beta r. Also, if we account the moment generated at point B, the moment is given by P, which is here, times the length of the beam divided by 2, and then you have a tangent theta to get the deflection in the middle section. Okay, so basically, so let me repeat. So for the moment generated at point B caused by the load P, it is given by P times this length, while for this length, for this deflection, it is given by L divided by 2 becomes this, right? And then tangent theta to get this. Okay, so here it is theta. Okay, so basically, if we assume tangent theta is equal to theta due to a small angle assumption, then this MP can become MP equals to P theta L divided by 2. So anyway, we want the moment generated by the external load P less than the critical load, the critical moment of the rotational spring. That is, we want P theta L divided by 2 is less than 2 theta beta R, and we can rewrite this inequality to be P is less than or equal to 4 beta R divided by L. So surprisingly, you can see the theta here could be cancelled out, right? So the critical load on the simple model, so it is a simple model of two rigid bars, okay? The critical load under the simple model is given by P critical equals to 4 beta R divided by L. Next, let's introduce you another model, which is the Euler continuous model by using the differential equations approach. So now we are going to derive the critical loads by Euler's continuous model. So just now, we assumed that there is a rotational spring in the midsection of this column, but in the real world, it is not really common to solve the column deflection or column critical load problem by using the simple model due to its lower accuracy and it is deviated from the reality. So by using the differential equations approach, we will able to get the moment inside the beam as well as construct the differential equation. Then we can get homogeneous and particular solutions. So for particular solutions, I will introduce you later. But for homogeneous solution, we have already discussed in section 8.0. That is, just now we have already solved an example of homogeneous ODE. And for particular one, I will introduce you in the example. So basically, it is about inhomogeneous ODE, but it is rather simple. And you are going to solve the unknowns generated while you are doing the problem. Then you get the general solution and compute the critical load. So next, let's discuss the first case of Euler's continuous model, which is pin-pin ends. We cut it and we get the moment inside the column. So for this column, there could be some deflection, and of course there will be deflection curve. So we denote the deflection curve as V. Okay. So inside the column, of course, in our previous chapter in tutorial 7, we mentioned that moment equals to EI V double prime X. But by figure C, which is located here, okay, by figure C, we can find that the moment inside the beam is given by minus PV. So V is the deflection over there, okay, and we have M plus PV equals to 0 due to the statics. So let me write clearer. M plus PV equals to 0 due to statics, and you got M equals to minus PV. Okay. Then after you get M equals to minus PV, then it will become purely mathematical things. So you put minus PV into here. Then the differential equation will become EIV to the second derivative plus PV equals to 0, and the V double prime plus P divided by EI, V equals to 0. So we are going to introduce a notation which is K squared equals to P divided by EI. So K later on, there is some meaning on it, okay? So such ODE now becomes V double prime X plus K squared V equals to 0. if we substitute v equals to e to the power rx, then we have r squared e to the power rx plus k squared e to the power rx equals to 0. So e to the power rx is cancelled out. What's left is r squared plus k squared equals to 0, and the solution will become r squared equals to minus k squared, then r equals to ik with plus minus sign. Okay, so we always assume that p is positive. ei, of course, is greater than 0, then k squared must be a positive number. Okay, so our solution of the characteristic equation falls to case 3, as we just mentioned, because the solution r equals to plus minus ik, although there is no real part, or we can say the real part of the solution is 0. So the solution of the characteristic equation is just the complex conjugate case. So the solution will become v equals to c1 sine kx plus c2 cosine kx. The reason of absence of e to the power something is that there is no real part in the characteristic equation, right? But anyway, by using our boundary conditions, v0 equals to 0, then we have c2 equals to 0. VL equals to 0, then we have sine KL equals to 0. So you just substitute the things inside the equation, then you get some results. So most important thing is sine KL equals to 0. So now, in what case does sine KL equals to 0? Well, we know sine theta equals to 0 when theta equals to 0, pi, 2 pi, etc., right? So we know that KL could equals to 0, pi, 2 pi, blah blah blah. So KL equals to n pi, where n equals to 0, 1, 2, blah blah blah. Okay? And finally, if we make P to be the subject of the K as what we just defined, so still remember we defined K squared equals to P divided by EI, so we make P to be the subject, then P equals to K squared EI equals to n squared pi squared EI divided by L squared for all n, and the equation of the deflection curve is given by C1 sine kx, k equals to n pi divided by L, as what we get over there. Okay, then you put it into the deflection curve. But if we are talking about the critical load, so in the real world column problems, we only consider n equals to 1, because for n equals to 2, 3, 4, the column could be the shape of something like this, but it is not that realistic. You know, when a column is subject to a load P, most probably the column will deflect in this way, something like this. Okay, it will not become something like this, you know, very hardly to happen, right? So we will take n equals to 1, then we can get the critical load of the pinned end situation, which is pi squared EI divided by L2 when we take n equals to 1. Okay, so the critical load for the pinned ends is given by pi squared EI divided by L2 by using the differential equations approach. Okay. So next, let's introduce you about the fixed free ends. So in this case, still we cut this beam at this somewhere, okay, and instead of taking this moment, we will take the moment like this, okay. So for this moment, you know, there is P located over there, okay, and the moment generated at your end is given by delta minus V. Okay, so the moment generated by this external load P is given by P times delta minus V. So if we use some magnifier, I hope I can make you clear. So here is delta, okay, and for this delta, you minus it by V, then you have the moment arm, which is located here. So the critical load times the moment arm, which is delta minus V, equals to the moment. So the moment equilibrium is mx equals to P times delta minus V. So now what we do is that we put this moment into the deflection curve differential equation and we rewrite it to be something like this. So still, if we simplify this differential equation by the assumption that k squared equals to P divided by EI, then the ODE will become V double prime x plus k squared V equals to k squared delta. So this time we are going to solve an inhomogeneous ordinary differential equations. So what we need to do is that we will first solve this ODE homogeneously. The thing is that we assume that the ODE now is V double prime x plus k squared Vx equals to 0 for the time being, okay? So we ignore this term first, and still we solve it as what we just mentioned, homogeneously, and still you will get this result, r equals to plus minus ki. So just now, by assuming that v double prime x plus k squared v equals to 0, you get a solution which is something like c1 sine kx plus c2 cosine kx. So it is called the homogeneous solution. But now you are dealing with inhomogeneous ODE, that is, you still have k squared delta on the right hand side. So what you need to do is to get a particular solution for this ODE. Well, we know that k squared delta is actually a constant, so we let Vp equals to C, let the particular solution of this ODE to be C, which is a constant, and we substitute into the equation. So we let Vx equals to C, and we substitute it into this equation. Then if a constant is differentiated with respect to x twice, then it will become 0. Okay, so the whole equation now will become k squared C equals to k squared delta. Then the value, the particular solution, will become Vp equals to C equals to delta. Okay, so the particular solution of this ODE becomes delta. Okay, so next, what we do is that we can get the general solution of this differential equation by summing up the homogeneous solution and the particular solution together. So for this portion, it is just the homogeneous solution solved by assuming that this ODE is homogeneous. Also, we have the particular solution, which is delta, then we just directly add it back. Okay, so the boundary condition now comes into our consideration. So at the fixed end, we have V0 equals to 0, which means that when x equals to 0, C1 is disappearing, okay, and the C2 times cosine 0, which is 1. Then this boundary condition will give you C2 plus delta equals to 0, which means that C2 equals to minus delta. We also have the boundary condition, which is V prime 0 equals to 0. To use it, we need to differentiate Vx with respect to x. So delta is a constant. What we do is that we get k out and we differentiate it with respect to x. So inside the bracket, it is C1 cosine kx minus C2 sine kx. So still we put v prime 0. So we put x equals to 0 into this equation. Then we will get C1 equals to 0. So eventually we will get the deflection curve, which is Vx equals to delta times 1 minus cosine kx. However, the deflection curve now has an undefined amplitude, which is delta. So although we have already assumed the deflection at the free end is delta, but we don't have any idea about what is delta. So we have to consider another boundary condition, which is at x equals to L, the deflection is given by delta. Then, by putting this boundary condition into our results in the previous slide, we will get delta cosine KL equals to 0. So, by solving this, it is either delta equals to 0 or
cosine KL equals to 0.
But delta to 0 is meaningless. We don't want to consider this case. Okay, so we are considering about cosine KL equals to 0. So to do this, for cosine KL equals to 0, we know cosine theta equals to 0. Theta equals to pi divided by 2, 3 pi divided by 2, 5 pi divided by 2, blah blah blah. So we can write, so here theta is just KL. So KL equals to n pi divided by 2, where n equals to 1, 3, 5, blah blah blah. Okay. Then we can compute P. Still, just now we have already assumed K squared equals to P divided by EI. So you put P to be the subject, and you get P equals to EIK squared equals to n squared pi squared EI divided by 4L squared, where K is just something like this, n pi divided by 2L, for n equals to 1, 3, 5, blah blah blah. Then the deflection of this fixed free ends case for the buckled mode shapes is given by delta times 1 minus cosine n pi x divided by 2L for n equals to 1, 3, 5, blah blah blah. And we can obtain the lowest critical load. The critical load is given by taking n equals to 1 of this equation. Then you get, for the fixed free end case, the critical load of the column is given by pi squared EI divided by 4L squared. Okay. So for two other cases of Euler's continuous model, fixed ends, and the fixed at the base pin on the top, they are rather similar. So one special thing I want to talk is about in the fixed at the base and the pin on the top case, when you do the differential equation and solve it all the way, you will find eventually you get KL equals to tangent KL, but this thing cannot be solved analytically, but we can get the solution of K by using some plots. So here as y equals to tangent KL minus KL, and for the horizontal axis it is KL. So we plot this diagram, and we get a point which is located here. So that means the first non-zero
Positive solution of KL is given by 4.4934 by using our numerical method by the plot. Okay.
And eventually you will get the critical load like something. So this is why the fixed at the base pin on the top case stands out to be the one of the most unique case in our column deflection Euler continuous model equations. So this one is very special due to it is impossible to solve this condition KL equals to tangent KL analytically. Okay. So In summary, for Euler's continuous model, we described or we discussed in detail by using the differential equation approach for two cases. So by using the differential equation cases, I orally described to you how to solve the critical load and the deflection curve for pin-to-pin column as well as the fixed free column. So for the fixed column, it is rather similar to the previous two cases, but for the fixed pin column, it is special case because for this one, it has something that is unsolvable analytically. So we used some numerical methods to get some equation. Looks very weird. So at the end of tutorial, here is an exercise for you to solve, which is columns with eccentric axial loads. So a lot of things are rather similar, except it has some eccentric axial load. So here is some hints. Once you get the moment inside the beam, so you cut the beam, you get the moment inside, you can get everything below the deflection curve, the maximum deflection, of course, in the middle, and the maximum bending moment. So all those things can be obtained by using the differential equations approach. So I believe if you are talented students, you could try it to solve this differential equation to derive those deflection curve or maximum deflection or maximum bending moment inside those important results by differential equations. So here I leave this example to you as an exercise. So because for this tutorial it's mainly talking about differential equations, it could be a little bit difficult for those who are not really good at differential equations. But anyway, in summary, I skipped two cases, the fixed end case, as well as the fixed at the base pin on the top case, those two cases, for your own reading. So basically, in this tutorial, we described some important results of critical loads, which is located here. And those equations will be important in tutorial 9 because we are going to use them to solve some problems related to the column buckling. Okay, so in the next tutorial, we will also introduce you some concepts about effective length, LE. Okay, so eventually you have three models. Again, to emphasize, you have a simple model, still remember? Consists of two rigid bars linked in the middle by the rotational spring, as well as pinned ends. Okay, and once there is some load applied on it, then there is some critical load, and surprisingly, the theta could be cancelled out. Also, we have the Euler's continuous model of four supporting types. Okay, so here there are four support types. Also, we have the columns with eccentric axial loads. No matter whether you can eventually derive those important results, those results will be important to solve some relevant problems. No matter whether you can or not use the differential equations, you should still bear in mind with these results. Okay? So thank you for watching tutorial 8, buckling of columns 1. And for this tutorial, it is mainly talking about the theory behind the differential equation things. So see you in the next tutorial about the applications of buckling of columns.